In this video, we're going to be taking a look at three force problems. We're going to be using Newton's second law, some force diagrams, and some different problem-solving methods to solve these three different problems. Now we have three different ones that get progressively more difficult, the first one being a little bit more simple, and the second and third one getting a little bit tougher, the third one being the most difficult. Now, all of them do have a very similar problem-solving method, but the way that they look is slightly different, and you'll need a little bit of different skills to be applied to each one of them. So the first thing you want to do for every problem is always draw your forces acting on the specific mass that you're looking at. So this one, there's just a block for each one. So we're going to have the regular force of gravity straight down. It's not on a surface, but it's talking about air resistance. So instead of maybe having a normal force, we have some air resistance going upwards. Now, since that's all we have, we're going to sum up the forces in the vertical direction, which you would either call the sum of forces in the y, or you call that F net y, both of which are the same. Now, when we're talking about vertical directions, I would typically say the one going upwards is your positive, and the one going downward is your negative. And then that always equals mass times acceleration, which is basically Newton's second law. So the only little formula you're going to need is that Fg is mg, the mass, times 9.8. So the force from the air resistance is going to be 20 newtons minus your mass of 5 times 9.8. And then that equals the mass times the acceleration. The mass is 5, and then the net acceleration is the thing that we're looking for. So if you take 20 minus the product of these two, which is 49, you're going to get a negative 29 equals 5 times a. And then if you go ahead and divide both sides by 5, then we have our answer. And our answer comes out to, I'll go ahead and write it off to the side, negative 5.8 meters per second squared. Okay, if something's in free fall, it would be negative 9.8 meters per second squared. So considering there's some air resistance, we're definitely looking for a number that is less than negative 9.8 meters per second squared as the magnitude of the acceleration. Okay, so there's the first one. So your step is definitely draw the forces and then sum up the forces along each of the axes, but we only had to look at the vertical axis, not the horizontal one, because there's nothing going on in the horizontal direction. Now for this one, we do have a force of gravity straight down. We have a normal force being pushed up from the floor to support the box. And then in addition, we have some other forces in the horizontal direction. It says 15 newtons are applied to it, so which could be to the right or left. I'm just going to choose the right. So we have an applied force, and I see a coefficient of kinetic friction. So that's going to imply that there is some kinetic friction as it's sliding. Now for this one, we're going to have to take a look at both of the axes. We have the sum of forces in the y direction. Again, our upward force is the normal force, and then our downward force is the force of gravity. That one we know equals 0. Okay, the reason why we know that's 0 is because there is no motion or acceleration in the vertical direction, so it's safe to assume that it's 0. Now for the forces in the x direction, okay, we have Fa as our driving force, and then the force of friction counteracting it, and that equals m times a. That will have some kind of a value that we are looking for. So let's go ahead and plug in these values. We have an Fg, which we know is mg, mass times 9.8. So I know that the 5 times 9.8 from earlier is going to be 49, so I'll just go ahead and grab that number. And then if we add that to both sides, that would mean that my Fn equals 49 newtons as well. So they're both 49. Now, in the x direction, that's the direction that's going to give us most of our information as far as what the acceleration is. So if we go ahead and plug in those numbers, we have the 15 newtons they gave us. And then also the force of kinetic friction is going to be the coefficient of kinetic friction times the normal force. So that normal force comes in handy up over here because we do need it for this part. We have the coefficient of kinetic friction as 0.2, and then times the 49 newtons of the normal force. and that equals m times a. Our mass, again, is 5 kilograms times a. So if I sum up everything over here, or actually subtract them, then I'm going to get 15 minus this force of friction over here, and then that's going to give us 5.2. Okay, and then from there, we can go ahead and divide both sides by 5. And then 5.2 divided by 5, I get an acceleration of 1.04 meters per second squared. I'll go ahead and write that over here, actually. Okay, so the only difference between the first one and the second one is really just more forces, and now you're looking at the x and y axis. Again, we're summing up the forces in the vertical direction, positive upwards, and then downwards is our negative. That equals 0 because there isn't any movement up and down. There is some horizontal movement, so we're going to keep the MA there so we can solve for an A value. But similar principles where we have something trying to move at the FA and then something opposing it, the FFK, the force of kinetic friction. And we did actually have to use some numbers from our y direction to help us with the stuff in the x direction so that we can find our force of friction. In the end, we were able to solve our acceleration. It came out to 1.04 meters per second squared. All right, now moving on to our last problem, let's go ahead and clear some space because this one is going to be a little bit more complicated. All right, now for this one, we have a few different forces. We still have our FG, we still have our normal force from the ground supporting it. And then we now have some force being applied upwards on an angle. And we still have some kinetic friction opposing the slide, so going back this way. All right, now here's the rule. We wanted to find the sum of forces in the x and y direction. If something does not fit perfectly in the x or y direction, then we have to find its components. So that's the first thing we're going to do. We're going to grab this applied force, and we know that it's 15 newtons, and we're going to create a right triangle with it. And then we're going to say that it has an x component over here, which we'll call FAX, and then it has a y component going upwards. We'll call that FAY. And then we know our angle from a little bit earlier. It's 20 degrees right over there. Okay, so what we're going to do is when we're looking for the FAY, because that's the opposite end of the 20, and we have the hypotenuse, we're going to use sine. So the sine of 20 degrees equals FAY over the hypotenuse of 15 newtons. And then you could multiply both sides by 15 newtons, and then your FAY comes out to 5.13 newtons. Now for your x component, it's going to look pretty similar, but we want the adjacent side and the hypotenuse side. So we're going to use the cosine of 20 degrees to get our FAX, put that over the 15, and then multiply both sides by 15, and then our FAX comes out to 14.10 newtons. Okay, our x component is definitely quite a bit larger because 20 degrees is much closer to being horizontal than vertical, so that sounds like it makes sense. Now let's go ahead and sum up the forces in each of the directions. We have the sum of forces in the y direction. For this one, we have the normal force going upwards. Okay, and then actually in my drawing, I'm going to add the FAX and the FAY in it so we don't forget to include those, because we're not including the FA because it doesn't fit nicely along one of the axes, so we're going to just grab one of these. So we have the FAN going up, we have the FAY going up also, and then we have just the FG going down. So these are two positive ones, and then we have an FG going down, and that equals 0 because the thing isn't rising off the ground, so there is no velocity or acceleration in the vertical direction. And then in the x-axis, or on the x-axis, we have the sum of forces going horizontally, which is just the FAX that is moving it sideways, and the force of kinetic friction that is counteracting it, and that equals m times a. Okay, so let's go ahead and plug in our numbers for the top portion and then move down to our bottom portion. All right, so I plugged in all of my values. We don't know the normal force. We knew the FAY, we found it earlier over here in green. And then we subtracted our FG, which is mg, mass times 9.8, which was 5 kilograms times 9.8. Now, if we combine these two, we get negative 43.87 that we added to the other side. So the normal force is 43.87. It doesn't have to support the full 49 newtons because it's being helped by this FAY over here. So that's why it's a little bit less than the normal force of the second problem. Now for the forces in the x direction, we have FAX, which we found in purple over here. And then we subtracted the force of friction, which is again mu times the normal force. Mu is 0.2 given in the problem, and the normal force we just found previously over here, 43.87. So we subtract those, and then we get 5.33 equals our m times a, dividing both sides by 5, and then we finish off with an acceleration of 1.10 meters per second squared, which is slightly greater than our previous one. So I purposely left some of the same, or most of the same values for our second one, besides changing the angle of the force. So this is a 5 kilogram mass being pulled with 15. This is a 5 kilogram mass being pulled at 15. And you might be wondering, well, if the FAX, the part that's making it slide, is getting broken up a little bit into our FAX and FAY components, why would it accelerate at a greater rate? And that's because it decreases the friction. So if you're taking an FAY and releasing some of the pressure between the ground and the object, you're going to decrease that force of friction. And then in the end, that decrease of friction is going to increase that acceleration. That's not the case in all different cases that are angled, but for some of them, it definitely is. So with all of these problems, you do definitely draw all your forces, and then you sum up everything in the x and y direction, assuming that there's forces along both of the axes. If you have something angled, you'll use something like a sine and cosine to break up its components, but then you make sure you put everything in your x and y formulas, plug it in, do a little bit of algebra, and then go ahead and find that acceleration. So I hope that was helpful to you in setting these problems up. Thank you for watching.